Hello everybody. This is the first of some videos about applications of integration. Let's start with a little trick. We can use the symmetry of a function to simplify the evaluation of its integral. Well, in certain cases, this only works if the lower limit of the integral is the negative of the upper limit, like in this case. If we have an even function, that is one which is symmetrical to the y-axis, then the area between minus a and a is twice the area between 0 and a. Often, evaluating the antiderivative at x equals 0 is very simple, so life gets a little bit easier for you. If the function is odd, life gets even better, for an odd function is point symmetric to the origin, so the area above the x-axis is exactly compensated by the negative area below the x-axis, and the resulting integral is 0 because the integral is the net area. I doubt whether this deserves to be called a theorem. It's more like a little trick. Let's have a look at example 1a. You write the integral as a sum of two integrals. Then x to the 4 is even, x to the 3 is odd. Hence, the first integral is 2 times the simple integral, and the second one is 0. Then you use the fundamental theorem. You only have to compute one single expression to get the result. We will skip the b part because it involves trigonometric functions. And please stop the video and as a warm-up do the exercises 7 and 9 on page 69 now. Next, there is an application of integrals which has nothing at all to do with areas. We want to find the average value of a function. Recall the average value of a few numbers. Here, the weight of 5 people in pounds. Of course, you know how to do this. You just add them together and divide by 5. Now suppose we have a function which is defined on the interval from a to b, say. It takes on lots of values, actually a whole interval of values. Does it make sense to talk about the average value of the function? I mean, we can't possibly add together infinitely many values and then divide by infinity. But can cut the interval into n subintervals of length delta x, as in the process of integration. Choose a point xk bar in each subinterval. Evaluate the function at these n x values, and then take the average of these n numbers as usual. Remember that we computed delta x by dividing the length b minus a of the interval by the number n of subintervals. We can also get n by dividing b minus a by delta x. If we insert this expression into the formula for the average, we will get a double fraction. Simplifying means multiplying the numerator by the inverse of the denominator, and this gives this expression here, which is nothing else but a Riemann sum divided by b minus a. If this is not immediately clear to you, stop the video and write this down with a concrete example. For instance, a equals 2, b equals 4, n equals 4. Now we can take the limit, and the result is this expression, the integral divided by the length of the interval. And this motivates this definition. The average value f bar of a function f is this expression. There's a nice geometric interpretation of this result. Multiplying this equation by b minus a gives this. So the integral is the area beneath the curve, and it has the same value as the area of the rectangle of width b minus a and height f bar. Here's a quick check. Stop the video and think about it. You should have gotten the answer as the constant itself for the constant function and 0 for the odd function. Here is another example which computes the average elevation of a hiking trail, which you can study for yourself. Here is a second and very important application. Let's suppose that we have an object which moves on a line. The function s of t describes its position at the time t. Position means the location of the object relative to the origin. We already know the derivative s prime of t is the velocity of the object, which may be positive or negative depending on whether the object is moving forward or backward. Now suppose we know the position of the object at 2 times, a and b, where b is bigger than a. So time b comes after time a. Then the displacement of the object is a difference s of b minus s of a. This displacement can be positive, as in the first picture, or negative, as in the second picture. We have learned that integration is the inverse of differentiation. If by differentiation we get the velocity from the position, then integration should give us back the position function from the velocity function. To begin with, if we know v of t and take the integral, then this means that we take the integral of s prime of t. But then s of t is an antiderivative, so by the fundamental theorem, the value of the integral must be the displacement. We can compute the displacement even if we only know the velocity function and not the position function s of t itself. Note that by knowing the starting point and end point of a movement, we don't know anything about the movement in between. It could be that it went like this, first very far to the right and then back again. Here is the velocity function of this movement. You start with a high speed, get slower until you stop, turn around, go backwards, come faster, and then stop. The area A1 tells us how far the object moved in the positive direction. The area A2 tells us how far it moved backward, and the net area A1 minus A2 is the displacement of the object. Don't confuse the displacement from the distance traveled. It is the same difference as between net area and total area. If you want to calculate the distance traveled, you need to integrate about the absolute value of the velocity, which would be the speed. In the box you can find a summary of the concepts which I talked you through, and example 1 you should study on your own. We're not quite finished because we wanted to get back the position function from the velocity function, but by now we only have the displacement. Here something similar to an area function comes into play. We look at the integral with lower limit 0 and upper limit t, so x here would be a dummy variable, then this is the displacement s of t minus s of 0, that is, position at time t minus position at time 0, or initial position. If we know the initial position, then we can just rearrange this expression and get an expression for the position function. Just add initial position and displacement. We will skip the example with the oscillations. You can study the example with a skydiver on your own. This is not just about positions and velocities. Whenever we know the derivative of something, how something changes, then we can back this something by integration. For instance, the acceleration is the derivative of the velocity. If we know the acceleration, we can find the velocity. And in general, if we know any quantity q and we know how this quantity changes, then integration gives us back the quantity itself. So q may be the mass of cells in a lab experiment, or the amount of water evaporated in the course of a day, as in the beginning of this unit. The fundamental theorem tells us how to compute the quantity itself if we know how this quantity changes. We need to skip example 5 because it involves exponential functions, but you can read example 6 about production costs on your own. Thank you for watching.